want to make sure I acknowledge that long list of collaborators there, and including the animals in the background there, which are nicely apt for this. That turned out to be a not exactly the right place to put an sensor, and we moved that one, but anyway. OINK stands for Ozark, Illinois, Indiana, Kentucky, which was an acronym or blame or credits go to Basil for that. I'm going to start with sort of the obligatory project. I could go on and bore you about all the original project goals, but I think this little picture summarizes some things that are good to start with, which is basically that the mid-continent, the premise basically is that it may be flat and featureless topography in a lot of ways it might seem, but there's an awful lot of interesting geology in the middle of the country that is largely unexplored. It's a much more of a frontier, really, an exploration realm than anything else that we've done a lot in the western U.S. And in particular, where the OINK study area is this area centered around the Illinois Basin, so there's a big emphasis on intercontinental basins and arches. So I'm going to start with just kind of give you an idea of the geometry of the setup. This is our typical site, just to look, anybody would see. This shows example of the cornfields. Just to give you an example of the kind of, and we use a lot of issues of cell phone telemetry. You see it on that particular thing. And we have this little cute little thing with FA volts and this little bag of mulch there, which actually turns out to be a nice little experimental setup. The experiment's been done in what we're calling 3 phases, actually. The first part, we started out actually over a year ago, almost 2 years ago, with mostly short period instruments and 9 broadband instruments that Purdue had, that's shown in this geometry, mostly along the, concentrated along the Ozark, Illinois boundary region between the basin. And this was mostly directed at seismicity problems, and I'm going to give you some results from that in a minute. And this is shown on a map. I guess these pointers don't work. It's shown on a map for the basement in the Illinois Basin. Now, since then, this is the geometry that's running right now. There are 70 stations there that expand from right about the Indiana-Illinois border into Missouri. All those are broadbands. This is where we're planning to move it to over the next 6 months or so. So there'll be a total of 140 stations. The design is basically a densification of the TA with a focus on crustal structure for the higher resolution that's provided by that. I wanted to just quick put this in there about in this particular area, telemetry is actually quite practical and very spectacularly successful in the sense that I like to point to this number that of the 52 telemetry stations, we're getting 99% data recovery, which is as good as the TA. The part of that is being able to we look at the data every day to make sure that's so, but that's an important thing. Anybody considering experiments in the eastern U.S. where you have cell phone coverage, do it. It's worth the effort. So the rest of this talk, I'm going to talk about some of our preliminary results, and we're along at various stages. So I'm going to start out with a poster advertising a poster that's by Steve and his student, Stephanie Domroys. And I'm just going to quick go through these. They've done this fabulous compilation of basement structure in the entire mid-continent. And so this starts with a fault map, which are the red lines here. Whoops, I went too far. Then there's you can stare at this map and this series of maps for a long time, so I strongly advise you, anybody interested in mid-continent geology, to go look at this stuff, because there's some fantastic stuff in here. That what we see here is a shaded relief of topography, of depth to basement. So the darker brown is deeper basement. Here he has an overlay, they have an overlay of surface geology, but this particular map is quite fascinating if you look at it, and I think there are two important conclusions, I think, that follow from this, which is, one is that intraplate earthquakes have this amazing concentration, which I don't think was really strongly recognized before, along these boundary systems where the basins are occurring. And in fact, if you looked at, is that going to show? Yeah. Where we're working here across the Illinois, from Missouri across the Illinois Basin, is only partly into really stable craton, if you will, that isn't pockmarked by scars of previous deformational episodes like this. So, moving on, the next thing I want to talk about is a poster advertised as from the phase 1 experiment. What we've done with that to date is mostly about seismicity, to clarify what we know about seismicity in that particular region. The background is that most people don't realize that there's a rather important extension of the New Madrid seismic zone there, shown as that SGFZ, which is a St. Genevieve fault zone that's been active historically. This is the regional catalogs data. And it's quite a significant activity level. In fact, I'm going to show you in a minute that in those two boxes, which are equal area, it's 1/3 the activity rate of the New Madrid region, and there's almost no instrumentation there by comparison. Here's the results we had from, which is not a large number, but of about 10 months of seismicity, basically. There are a total there of a big grand number of 20 identified earthquakes, although there's probably something on the order of 2,000 mining explosions. What we see is that what we see is this a cross section on the right and a map in the middle. And one way that's important about that is that the depth distribution in this region is actually noticeably different from New Madrid. On the left is the the regional catalogs results of the same thing, of depths over a long time period compared to the depth distribution in New Madrid. And we have a smaller event count, but we confirm the same kind of thing, is that there's a noticeable difference in the depth of seismicity in this particular region. And this is a very complicated figure, and I won't dwell on it. You should go look at the poster if you want to stare at it. But the bottom line of it is that if you normalize for area and time period, and we comparing data from the regional catalog to ours, we get a consistent activity rate, and it's for our experiment compared to the regional catalog. And the rate in the St. Genevieve region is about 1/3 of the New Madrid region, which is significant considering that there's the instrumentation that exists there is pretty minimal. So the next part of this is some results on various forms of two different versions of P receiver function imaging. The first thing I want to show you is some brand new results that are only a couple weeks old that I got from Hirsch on the crust, and then I'm going to show you a bigger scale image in a little movie on the relationship to a larger scale, mostly from strictly TA data that looks more at lithospheric scale. So first, this is kind of a zoom into Steve and Stephanie's map, I should say, of the structure in the Illinois Basin. So that you see the depot center is along the Illinois-Kentucky border there, and that little red is where outcrops in the Ozark Dome occur. And the result that's really interesting about crustal structure is, if you could see behind there, I could go back and forth from these, and it's too slow. These are exactly on the same scale. Does my pointer sort of work? If you read those lines, there's 50 kilometer thick crust into this region to the northwest, and under the Illinois Basin, it's more like 45. And where'd I go here? So that transition occurs right along this boundary at the edge of where the deepening of the Illinois Basin occurs. So it strongly indicates that strongly suggests at any rate that that's a crustal scale feature that's driving that part of the basin deformation. This is, why did that get butchered like that? I didn't notice this one. It got turned sideways. I was supposed to show you the weird, okay. This shows the seismograms, but you can't really, they're sideways, so we're gonna have to just deal with it. Anyway, it's just showing the data that went into that and shows that we really have a nice, clear MOHO signature and that's not fantasy up there. Now, the next part of this is a demonstration, I think, of how any experiment doing this kind of thing typically will merge larger scale data from the bigger array, the TA, in with a more high resolution study like ours. At the moment, what I'm going to show you is a result from just the TA. We haven't combined it with our data yet, but that's down the road. What I've got here is a fully 3D migration method that's been applied to this data. And what's a little bit different about this is it's a nerdy detail, but it's important. I've applied a crustal multiple removal method that I just got working a little while ago to try to remove the crustal reverberation. And the reason that's important, I'll dwell on in a minute here. I'm going to play this once, and then I think, well, I better just play it. Well, that doesn't work, does it? Let's see, click on it, I guess. So what we're going to do is I'm going to have to do this on the movie player, I think. So what we're looking at here, this is the 410, and this is the 660. It's this feature here, which I used to think was nothing but a multiple until I applied this multiple removal procedure. But it doesn't go away when the crust, which is associated with it, largely goes away. So I am beginning to think this has some relationship to a well-known feature that's commonly seen in S-wave receiver functions. It's been used for what's called the LAB, estimated by that method. And normally the P problem is contaminated by this multiple problem. So the jury is partly I'm not completely closed on that, but I think there's an interesting, let me see if I can figure out how to play this again. Now you saw it once, and I will quickly finish here. So you notice this starts out with topography. It's going to fade to the basin background to show that relationship. This is all in true 3D geometry, by the way. And then there's crustal, then you see Hirsch's crust map fade into view, and then I'm going to turn and rotate this thing. So that's the basement model. There's the crust fading in, and now we're going to look across here. So I want you to look at, I'll close on looking at this, that there's a hint that the LAB, if that's what it is has interesting structure in the vicinity of the whole Illinois Basin and the rift system. And if this holds up, it's quite an interesting result. There's also some very interesting structure in between the 410 and the base of the crust as well, but I don't have time to go into that. So the last thing I'll just quickly blow by, which is we've got early phases of P-wave tomography that we're working on. I don't have a model to show you yet, but I do want to show you that we have a surprisingly large signal. To me, it's a surprisingly large signal because it's as big as large parts of the western U.S. This is an average, just shows you an example of an average of residuals we determined from sort of Northeast Pacific sources. And the bottom line is we got about 0.8 of a second of P-wave residuals and very consistent patterns we see from different directions. So there's likely, we should have every reason to think we have a nice mantle signature here, and it's too big for the basin. I don't show you those calculations, but we calculate that the basin effect, from what we know, the stratigraphy is totally known in the Illinois Basin, and if you strip out the effect of the sediments, it's only about 0.2 of a second. So that signal is significantly larger than that. Just a quick thing to show you how that's a map showing how the residuals, the fact that the colors are comparable from different source regions is a really good sign that the data has got a lot of integrity to it. So we're hopeful that that's going to yield a really interesting P-wave model. And I didn't want to do that, but that's okay. So, and I will close this. I don't never believe in reading my conclusions. There they are. You can read them, and I don't know if we have time for questions or not, but that's the summary of everything I talked about. See the posters. There's a couple good ones up there, especially stare at Steve's map. That's really interesting. Oh, thank you.
Time for one question.